Hi again, everybody. Mr. Kolakowski here. This lesson is about total internal reflection. Let's start with Snell's law. Okay. Snell's law is a concept that comes out of this principle of refraction. So, Snell's law says that you have light starting in one medium, and that light is going to enter another medium, say from air into water. And the equation is here we have n is the index of refraction. Let me go ahead and remind you what that is. N is the ratio between the speed of light in a vacuum and the average speed of light in the particular medium that you're moving that light into. Okay, so we have the index of refraction, the incident, we have the index of refraction, the refracted part. A lot of times this equation is written like this. Let me show that to you here. N1 sine theta 1 equals N2 sine theta 2. It's the same thing where 1 and 2 represent the different mediums that the light is going from and into. So anyway, the main equation is N1 sine theta 1 equals N2 sine theta 2. The light is going from one medium to another, and it's bending, it's refracting. So what this lesson is, it's going to be a discussion of a special case of Snell's law. Uh, I'm going to couple this video with another video or two that gives you some real world reasons why this is a really important topic to know about. Fiber optic cables and things like that kind of come out of this. But what we want to do is focus on the main science and try to understand why light bends in the exact mathematical way that it does, okay, when it goes from one medium to another. In this case, it's a special circumstance of refraction called total internal reflection. Okay, now, if we look at this equation carefully, uh, Snell's law, we'll say at a certain point, okay, so okay, um, this second theta, the theta 2, okay, is going to be equal to 90 degrees or more or greater, okay? So in other words, when that happens, we'll say the refracted light, the light that is bent, the refracted light will not enter the second medium, okay? So with this, I'll link a video demo for you guys. Let me see if I can draw this for you. And of course, you can let me know if you have any questions on anything. Let's start with a couple of pictures, okay? Let's see if we can get this to make a little bit more sense, okay? So let's start with, by the way, let me add a couple of details up here. So the index of refraction for air is 1.000293. Okay, so basically 1.0. And the index of refraction for water is 1.33. And we've looked at that in a previous lesson. Anyway, those are the two values that you'll need to know for this. Okay, so in this particular case, let's see if we can explain what's going on. We have, in fact, I can color this a little bit. So we have water. Okay, let's start over here. Let's go back to this original color. So I'm going to draw the normal line like this. Okay, so these are the normal lines. These are going to be three different scenarios here. Okay, so in our first picture here, I want you to imagine. Let's use. So this is the air side. This is the water side. Okay, so you've got air up here, water down there. And let's imagine we're going to start the light from the water side. Okay, so the light ray comes in like this. Okay, and here we have our theta 1. Okay, now what happens with refraction is that when you're going from a more to less dense medium, you're going to bend that light sort of in this direction. Okay, so this is going to be our theta 2. And again, this is just refraction. So this isn't total internal reflection or anything. Right now, this is just good old-fashioned Snell's law. We could calculate theta 2 if we knew what theta 1 was by using Snell's law. Okay, now what happens though at a special angle, we call it the critical angle. All right, so let me see if I can, that's what's going to happen here in the second picture. So the angle here, so this is the light ray coming in. We're going to call this theta. We'll call this the critical angle. I'll put a little C down there, okay? The critical angle. And what happens is that refracted light stays right there, okay? In other words, this is 90 degrees, okay? So this is the special angle upon which the light isn't going to get into the air. It's going to stay down here in the bottom half of the picture, okay? Now, if you continue this process, let me draw one more picture for you guys here. Let's imagine that we're at an angle that's larger than the critical angle, something like this, okay? What happens is you just get reflection, okay? You're going to get the law of reflection kicking in like this, okay? In other words, here's theta 1, here's theta 2, and now we have total internal reflection. But you have to have this theta be larger than the critical angle, okay? So let me write that down over here for you guys. Okay, we'll say it like this. When the incident angle, or theta 1, is equal to, or let's say it's greater than the critical angle, okay, critical angle, okay, you're going to see total internal reflection, okay? Basically, you're no longer using, well, I don't want to simplify this too much, because in the demos that we do in the classroom and that you'll see on YouTube, it's not a 100% process where all of that light is, perfectly translated off of this this surface here. But for all intents and purposes, okay, the angle here, right? This is just the law of reflection. So here's your light coming in. The light is going to make it right back to it's going to stay inside that water in this case. Those two angles are going to be the same, and you're going to get this really beautiful reflection. This is why scientists can then, work with engineers, and the engineers can design some amazing, amazing things from the physics of this special case of Snell's law. The big one are fiber optic cables, and I have a video that I want you guys to watch. This is a really amazing application of some basic physics, and fiber optic cables, which is an application of total internal reflection, is a really amazing thing to learn about. Now, I want to show you how to find, last thing here, winding this video down, is I want to show you, maybe the most important thing here, is how to find the critical angle. Okay, how do we do that? How do we find what this is? And if we go back to, you remember the context of this particular example is we have this down here is all water, okay? And then up here this is the air side, right? So up here is the air, down there is the water. So the question becomes, how do we find the critical angle? What is going to be that special angle of incidence that's going to cause this scenario right here, which in turn uh, basically tells us, once we know what that critical angle is, we can then determine how to make sure that total internal reflection takes place. Because once we know what that critical angle is, anything that's larger than that critical angle is going to allow us to have this total internal reflection uh, emerge from the scenario. Okay, so let's finish up by finding the critical angle. Let me show you how to do that. So we're going to do a little math problem here. Okay, so let's start with, so here's Snell's law. So if we look at the situation very carefully, we're starting in the water, and the index of refraction of water is 1.33. The critical angle is that angle of incidence, so we're going to leave that as our unknown, okay? Then on the other side of the story, we're going to have air. If you remember, air is on the top half of the picture. So that's going to be 1.0003 or 1.00. If we go back to this picture right here, you'll notice that this is 90 degrees. Okay, that's going to be that refracted angle that allows us to sort of see that barrier between refraction and reflection. So that's going to be the sine of 90 degrees. Okay, so all that's left for us to do is to grab our calculator and to solve for the critical angle. Why don't I give you a few moments to do that? You can hit the pause button. If you hit pause, welcome back. The correct answer that you get solving for this, you do have to use the inverse sine function on your calculator, is 48.8 degrees. Okay, so that means any angle of incidence that is greater than 48.8 degrees, you're going to get TIR as your result. And the light ray will not actually leave the water. The light will stay within the water and basically look like this picture right there. All right, everybody. Let me know if you have any questions. I hope you're doing well. Talk to you again soon.